You know, I think we usually think of memory as like just a brain thing.
Right.
You touch a hot stove, your brain remembers the pain and, never to do that again.
Yeah.
But your body, on a microscopic level, actually has a physical memory that operates entirely independently from your brain.
Yeah, it really does.
And realizing that fact back in the 18th century is essentially what allowed us to pull off what I think is the greatest biological heist in human history. So, welcome to the deep dive, everyone.
Thanks for having me. And it really is a heist, honestly.
Right. Today, our mission is to take a really comprehensive, unhurried look at the fundamental science and the history of vaccines. We're stripping away the jargon so you can understand exactly how they work. Because we all hear about vaccines in the news, but, understanding the actual mechanics gives you a completely different perspective.
Oh, totally. It shows how human ingenuity basically hijacked a natural biological process. Because if you survive a natural infection, you often can't catch that exact same disease again.
Right, because of that physical memory.
Exactly. Specialized memory cells, B cells and T cells, they persist in your bloodstream and your bone marrow. They stick around, sometimes for decades, just primed and ready to respond incredibly fast if that specific pathogen ever tries to return. So you get the memory and you get the protection.
But the historical catch there was brutal.
Right.
Acquiring that memory the natural way meant you actually had to survive the disease first.
Yeah, that was a catch.
And for most of human history, that meant facing a very, very meaningful chance of death
Yeah.
or just permanent, life-altering harm. You essentially had to gamble your life for the immunity.
Which is why the whole concept of a vaccine is so elegant. At its core, I mean, it is simply a way of obtaining that specific immune memory without having to endure the actual illness. You get the memory, but you skip the disease.
Skip the line entirely.
Exactly. And what's fascinating is that the history of this breakthrough starts entirely with observation, like long before we had any actual scientific theory to explain it.
We really have to go back to an 18th century English country doctor for this, Edward Jenner.
Right, Joe.
He didn't have a microscope. He had no concept of genetics, obviously.
Yeah.
But he paid attention to this widespread piece of local folk knowledge. People noticed that milkmaids, the women who milked cows for a living, frequently caught a mild disease called cowpox from the cattle.
Yeah, just a mild, annoying rash, really.
But the crucial observation was that milkmaids who recovered from cowpox seemed entirely bulletproof against smallpox. And smallpox was no joke.
Oh, smallpox was an absolute terror. When you look at the historical data, it was killing roughly a third of the people it infected.
Wow, 1 in 3.
1 in 3. And for those who did survive, it routinely left them permanently disfigured or even blind. It was devastating.
So in 1796, Jenner just decides to test this folk knowledge. He takes material from a cowpox sore, inoculates a young boy, lets him recover from the mild cowpox, and then deliberately exposes the boy to smallpox.
Which is pretty wild by today's ethical standards.
Very wild. But the boy didn't get ill. Jenner proved the concept. And just as a quick side note for you listening, the word vaccine actually comes directly from this experiment.
Yes, it derives from vacca, which is the Latin word for cow.
Right, in honor of the cowpox.
Yeah.
It makes me think of, like, using a smartphone today.
How so?
Well, you can hand a phone to someone, and they don't need to understand anything about microchips or wireless frequencies or, the binary code to make a call. They just need to figure out which buttons to push on the screen to get a reliable result.
Oh, I see.
Jenner essentially found the biological buttons to push, even though immunology literally didn't exist as a science yet.
That is a great way to frame it. He found the interface, but he didn't know the code. Germ theory, the idea that microscopic organisms cause disease, that was still decades away.
Decades.
Yeah. But that observation was enough of a foundation to build on. And just to fast forward to the ultimate conclusion of Jenner's work, smallpox was officially declared eradicated in 1980.
Which is incredible.
It is. It remains the only human disease we have ever deliberately wiped off the face of the earth.
So Jenner gave us the effect. But what is the actual biological mechanism inside the body? Because once we started to understand the code, the underlying cellular mechanics, we didn't have to rely on lucky accidents like cowpox anymore.
Right. We could start engineering the interface ourselves.
Exactly. We had to figure out how to give the immune system a target.
And that target is called an antigen. The goal here is obtaining immune memory without the illness, right?
Right.
So think of the antigen as the active ingredient. It's a specific molecular structure, usually a protein on the surface of a virus or bacteria, that looks enough like the dangerous pathogen for your immune system to learn from it.
But it's incapable of causing the disease itself.
Precisely. It's safe training data. And over the years, we've basically developed four main engineering strategies to deliver this training data.
Okay, let's break those down because I have a sort of fire training analogy in mind for these 4 types.
Oh, I like analogies. Let's hear it.
Okay, so the oldest method we have is the live attenuated vaccine. In my analogy, this would be like putting the fire department through a controlled burn. It's a real fire, but it's artificially contained.
That is highly accurate, actually. Attenuated just means weakened. So you take the real live pathogen and you grow it in a lab under very specific conditions.
Weaken it.
Right. You force it to mutate and adapt to an alien environment. By the time you put it into a human, it's so weak that it replicates very, very poorly.
In vaccines like measles, mumps, rubella, they're designed this way, right?
Yes, and chickenpox too. Because it's a real replicating infection, the immune response is massive. The memory it forms is typically lifelong. I mean, a couple of doses of the measles vaccine, and you're usually set for decades.
But there's a trade-off there. Because a live virus, even a weakened one, is still a replicating threat. So you can't give a controlled burn to a forest that's completely dried out.
Exactly. You wouldn't give a live attenuated vaccine to someone with a severely compromised immune system, like a patient undergoing chemotherapy.
So to protect them, you need strategy number 2, which are inactivated vaccines. And in our fire training analogy, this would be like having the fire department practice putting out a completely fake dummy fire. There's no heat, no real danger at all.
Spot on. With inactivated vaccines, you take the pathogen and you completely destroy its ability to replicate, usually using heat or radiation or chemicals.
So the structure is there, but it's dead.
The physical structure is intact for the immune system to recognize, but yes, the pathogen is dead. But that creates a new trade-off. It is much safer, but because the pathogen isn't replicating, the immune system doesn't mount nearly as aggressive a response.
Because it doesn't view it as a 5-alarm fire.
Right. The memory it forms is weaker. Because of that, inactivated vaccines, like the polio shot or the rabies vaccine, they usually require multiple doses or boosters.
Just to remind the immune system of the threat. Okay, so if a dead virus gives a weaker signal anyway, do we even need the entire virus body? Strategy number 3 is subunit vaccines, which I imagine is like, instead of a dummy fire, you just bring the firefighters a single piece of a burnt log to study.
That's a perfect way to visualize it. You abandon the whole organism entirely. You just use a single fragment, like a highly characteristic surface protein.
And that's things like the Hep B and HPV vaccines.
Yes. It is incredibly safe because there is zero genetic material from the pathogen. It physically cannot replicate. But the biological hurdle here is that if you just inject a harmless little piece of a burnt log into the muscle, the immune system might just ignore it entirely.
It doesn't look dangerous enough to care.
Exactly. So you have to manufacture a sense of danger. And you do that using an ingredient called an adjuvant.
An adjuvant, okay, what is that?
They're fascinating. They are specific compounds, sometimes aluminum salts or synthetic molecules, that basically mimic the biochemical danger signals of a real infection.
So they act like local fire alarms.
Yes. They create a localized, harmless irritation at the injection site. This triggers cellular alarms that physically recruit specialized immune cells to rush to the area.
And when they show up to investigate the alarm, they bump into the burnt log.
They bump into the protein fragment, recognize it as foreign, and carry it back to the lymph nodes to build the memory.
Wow. Okay, so we've gone from a controlled burn to a dummy fire to studying a burnt log. But strategy number 4, mRNA, which obviously gained massive prominence during COVID, is a totally different ballgame.
It is a profound conceptual shift.
Yeah, in my analogy, mRNA isn't a fire at all. It's like emailing the fire department a detailed blueprint of the exact weapon an arsonist is planning to use so they can build a harmless model of it themselves.
That is a great analogy. We are no longer delivering the antigen. We are delivering the instructions for the antigen. The vaccine contains a strand of messenger RNA, which is essentially just a line of genetic code. It holds the precise recipe for building one single protein from the pathogen.
But RNA is super fragile, isn't it?
Highly fragile. It would be destroyed instantly in the bloodstream. So it's wrapped in a microscopic bubble of fat called a lipid nanoparticle. This fat bubble merges with your cells, slipping the mRNA code inside.
So your own cells read the instructions and manufacture the single protein.
Mechanically execute the code, yes. They print out the viral protein, push it to the surface of the cell, and your immune system spots it and learns it.
And we really need to pause and debunk a massive myth here. Because this exact mechanism is why the common fear that mRNA alters your DNA is, well, Biologically impossible.
Completely impossible. Your DNA is stored inside a highly secure, locked vault in the center of the cell called the nucleus. For a molecule to get inside, it requires very specific molecular passcodes.
Passcodes that the vaccine mRNA simply does not have.
It doesn't have them. It physically cannot cross into the nucleus. And furthermore, your cells are packed with enzymes whose entire job is to hunt down and shred free-floating RNA. Within a matter of days, the vaccine mRNA is completely degraded and recycled.
It leaves zero trace.
Zero trace. But the huge advantage of mRNA is speed. Because it's just code, you don't need giant vats to grow live viruses over months. You just need a chemical synthesizer.
So you can design a candidate in days from a genetic sequence.
Over a single weekend, theoretically.
That's incredible. Now, because these vaccine types differ in strength and design, they don't all last the same amount of time. Which brings us to why some vaccines are one and done, and others require you to keep coming back for boosters.
Right. There are three main reasons immunity fades or fails. The first is that the pathogen itself mutates fast.
Like the flu.
Influenza is the master of this. Its surface proteins are constantly shifting. The facial recognition software you trained last year is looking for a suspect that just doesn't exist anymore. That is why the flu shot requires annual reformulation.
Whereas measles is genetically stable.
Highly stable. Its face doesn't change, so childhood immunity stays relevant your entire life.
The second reason goes back to the engineering trade-offs. The vaccine type might just provoke a weaker memory, like we saw with inactivated versus live vaccines.
Exactly. And the third reason is just that immune memory naturally wanes over time. Tetanus is the classic example here. Your antibody levels drop over the years, so you need a booster roughly every decade.
Okay, that makes sense. Now, I want to clarify something about how we measure the effectiveness of these vaccines, because the statistics are routinely misunderstood.
Oh, absolutely they are.
You'll read a headline saying, a new vaccine is 95% effective. And I think the intuitive leap people make is absolute risk. They think, okay, if 100 vaccinated people are exposed, 95 are perfectly safe, and 5 will get sick.
And that is mathematically incorrect.
Right. It means a relative reduction in risk, doesn't it? Let me try another analogy here. Let's look at seatbelts.
Okay?
If I tell you a seatbelt is highly effective, I'm not guaranteeing that in 100 car crashes, you will walk away without a scratch 95 times.
Definitely not.
What I'm telling you is that wearing the seatbelt drastically reduces your relative risk of suffering a fatal injury compared to a driver who isn't wearing one.
That is exactly how vaccine efficacy works. The vaccinated group experienced 95% fewer cases than the unvaccinated group under the same exposure. And that distinction highlights something critical. You have to look at what outcome is actually being measured.
Right, preventing infection altogether versus preventing severe disease.
Exactly. Headlines often confuse the two. A vaccine might only be moderately effective at preventing you from getting the sniffles. But that exact same vaccine might be incredibly effective at preventing severe disease, hospitalization, and death.
Which is, generally the primary public health goal. Keeping you out of the ICU is a massive victory.
Exactly.
And understanding that this is about risk reduction on a grand scale leads us perfectly into what happens when you zoom out from the individual and look at an entire community.
Herd immunity.
Yes, herd immunity. It breaks the chains of transmission.
It's the ultimate mathematical shield. It protects those who literally can't be vaccinated. Newborns, chemotherapy patients, people with immune conditions.
But the math behind it depends heavily on the specific disease, right?
Yeah.
There's a metric called R0.
Right. R0 or R0. It's the average number of people one infected person would infect in a fully susceptible population.
And the formula for the required immune threshold is basically 1 minus 1 over the R0. So let's look at measles.
Measles is astonishingly contagious. It has a massive R0 of 12 to 18. One person infects up to 18 others.
Wow. So if you plug an R0 of 18 into that formula, the required immune threshold for the population sits at roughly 95%.
Which means the margin for error is razor thin. That's exactly why measles is the very first disease to return when vaccination coverage in a community slips even a little bit.
Because the shield cracks. Now, speaking of the shield, I want to pause and talk about the physical experience of actually participating in that shield, because we shouldn't dodge the reality of side effects.
We absolutely shouldn't.
When I get a shot, I often get a sore arm, I feel exhausted, and I might even run a mild fever for a day. And instinctually, my brain says, well, the vaccine is making me sick.
It's a natural instinct, but it's biologically backward. A sore arm, tiredness, or a mild fever is not the vaccine going wrong. It is your immune system responding, which is the whole point.
Wait, so if the fever and sore arm are just proof that my immune system is taking notes, Should I actually be happy that I feel a little crummy for a day? Is feeling gross actually a success story?
Yes, absolutely. It is the biochemical proof that your immune system is successfully executing the training drill.
Okay, that changes my perspective completely. But we do need to address serious adverse events too.
We do, and acknowledging them is vital. Serious adverse events genuinely do happen, but they are incredibly rare. We are talking one in hundreds of thousands to one in a million doses.
And we have systems to track that, right?
Very mature global surveillance systems. If a risk emerges, it's caught. But the key is that the risk of the disease itself is always much, much higher.
And while we're talking about safety, we have to debunk the MMR autism myth because it's still out there
It stems entirely from a retracted 1998 paper.
by one doctor.
Yes, and when you look at it, it was based on just 12 children. 12.
That's a tiny sample size.
It is. Furthermore, he had undisclosed financial conflicts of interest. He eventually lost his medical license, and the journal formally retracted the paper.
And what have the studies shown since then?
Subsequent studies of millions of children across multiple countries show a totally consistent answer. There is absolutely zero association between vaccines and autism.
So when safety, high effectiveness, and mass population uptake align perfectly, we can aim for that holy grail of epidemiology we mentioned earlier, making the pathogen disappear forever.
Eradication.
Why was smallpox eradicated but not other diseases?
Because three specific conditions have to line up. Condition 1, it must infect only humans. There can't be an animal reservoir to hide in.
Makes sense. If it lives in bats or pigs, it'll just keep coming back.
Exactly. Condition 2, the infection must be visibly identifiable so public health workers can contain cases.
And condition 3 is obviously an effective vaccine.
Right. Now, polio nearly meets all three. We have pushed it to the absolute brink. But human conflict and access difficulties in remote areas make that final step stubbornly hard.
And then contrast that with influenza.
Influenza fails the first condition entirely. It lives in birds and pigs, continually mutating and re-entering human populations. We can't eradicate it with current tech.
So let's bring it all together for everyone listening. Vaccines basically exploit a biological quirk of our immune memory. We've gone from a country doctor observing milkmaids to literally delivering genetic instructions inside lipid nanoparticles.
And all of it is designed to reduce relative risk and protect the vulnerable members of the herd.
It really is an amazing journey. But before we wrap up, I want to leave you, the listener, with a really fascinating thought to mull over. We talked about the mRNA timeline.
The speed of it.
Right. If mRNA technology allows us to design a vaccine candidate in a matter of days simply from a genetic code, what does that mean for the next time a pathogen tries to jump from an animal reservoir to humans?
It's a huge question.
Could we theoretically reach a point in the future where we have the vaccine ready before the first major outbreak is even officially noticed?
To essentially stop the pandemic before it ever really starts. It's an incredible prospect.
It really gives you hope for the future. Well, that's all for today's deep dive. Thanks for listening, and we'll see you next time.